Hello, thank you for having me. I'm Sam Pallister. I'm the Director of Quantum Applications at PsiQuantum. And if you haven't heard of PsiQuantum, let me just give you a 30-second summary. So PsiQuantum is a quantum computing company based in Silicon Valley, California. We develop both quantum computing hardware and quantum computing software. We're a fairly large company now. We're just over 225 people. Primarily based on the west coast of the United States, but also based in Europe and Asia as well. And there are two things that make PsiQuantum slightly unusual in the quantum computing space. One is with respect to the hardware. So the hardware approach that PsiQuantum pursues is to build qubits using silicon photonics. So that's to use light as qubits. But on the software side, we're unusual in that our singular focus is on large-scale, error-corrected quantum computers. And as a practitioner in this field, as an expert in quantum algorithms, I'd like to paint for you a realistic and explicit picture of what we think the capabilities are of both near-term quantum computers and quantum computers that are coming in the immediate future. And in particular, I'd like to try and convince you of three things over the next 20 minutes. The first is that useful applications, and by useful applications I mean applications that are commercially relevant, as far as we're aware, require large-scale quantum computers that are capable of carrying out error correction. And the second is that the era that we're currently in, which is known as the NISQ era, the noisy intermediate scale quantum era, deploys a tangential family of algorithms. And so the expertise that you might develop now in building and deploying NISQ algorithms is fundamentally different to the expertise that you would need in the fault-tolerant era. And lastly, I'd like to try and convince you of the fact that if we're going to exploit the full potential of large-scale quantum computing, which is the era that we will be in soon, we have to co-design quantum algorithms with domain experts. It's not enough for quantum algorithms and application specialists to operate in a vacuum. And so for the agenda for the rest of this talk, I'll go through these points in turn. But before we get there, let me just explain some nomenclature. So quantum computers today fall squarely into the NISQ era. NISQ quantum computers are severely limited in the number of physical qubits they have access to, but they're also severely limited in the number of operations they can perform. So on this slide, I've indicated the number of physical qubits on the y-axis, the number of operations or the number of gates that can be performed on the x-axis. So this limitation in the depth of circuit and the number of qubits is resolved by NISQ devices by repetition. And in fact, NISQ algorithms repeat in two ways. The first is to note that the output of a NISQ circuit is stochastic. It's noisy. And so this NISQ circuit is repeated many times in order to build up statistics with some confidence about the output of this circuit. But it's also repeated in a different way too. So in fact, it's repeated in a way that requires running a whole family of different NISQ circuits, where the parameters that go into the input to the NISQ circuit are somehow optimized in some way by some classical computation that sits outside in order to hopefully converge the operation of this circuit to some useful quantity that you want to calculate. So maybe it's some equilibrium property of some molecule that you're interested in if you're in chemistry and materials. Maybe it's the output to an optimization problem if you work in logistics, for example. Fault-tolerant algorithms, on the other hand, don't have this repetition. You run the circuit once, you receive the output at the end of the computation. And to be clear about the difference in scale between what we have now and where we'd like to be, this is broadly the difference between NISQ algorithms and fault-tolerant algorithms in terms of scale. And just to be clear, this is a logarithmic axis on both the x and y directions. So the NISQ computers that we have access to today, we can reach about 100 qubits, physical qubits. We can carry out, if we're lucky, maybe 100 operations. Quantum computers in the fault-tolerant era When we're targeting commercial applications, we typically think of machines with millions of physical qubits and with the ability to carry out billions of operations. Now, a fault-tolerant quantum computer doesn't require a million physical qubits because it's somehow encoding a computation over a million variables or something similar. We need that many qubits because to go from a computer that can carry out hundreds of operations to one that can carry out billions requires quantum error correction. And the price you pay for quantum error correction is some multiplicative overhead where you encode logical qubits by redundantly using many physical qubits. And typically that overhead is about a factor of 1,000 or so, according to our best estimates of error correcting codes. And so a fault-tolerant quantum computer with 1 million physical qubits encodes many hundreds or maybe 1,000 logical qubits. And so that's the scale of machine that people target in the fault-tolerant era. And this singular focus of PsiQuantum on fault-tolerant quantum computing used to be a niche opinion in the field. And that is now no longer the case. It's in fact the consensus amongst large companies in quantum computing. So let's just take the 4 largest companies I could find with publicly available roadmaps. Google, IBM, IonQ, and Rigetti, all companies based in the US. And you can see that based on the roadmaps that these companies have published, they're all trending towards the million qubit regime by the end of this decade at the latest. So to be explicit, Google plans to have 1 million qubits by 2030. The next milestone on their roadmap is to produce a single logical qubit. So they're putting quantum error correction at the forefront of their roadmap. IBM, we saw the roadmap yesterday. They plan to have 10,000 qubits and have implemented quantum error correction by 2026. IonQ plans to have rudimentary error correction by 2025, and Rigetti are already carrying out theory projects to develop error correcting architectures. And so really, you don't need to bet on every single one of these companies succeeding if you're willing to accept that we're going to transition fairly soon into the fault-tolerant era. And so if we're expected to derive quantum advantage in the NISQ era, we have until 2028 or 2030, not only to prove that quantum advantage exists, but to exploit it for commercial benefit. Because as soon as we transition to the fault-tolerant era, that advantage is gone. Okay. All right, so to give you just a flavor of the distinction in capabilities between NISQ devices and fault-tolerant ones, and to explain why PsiQuantum and the companies on the previous slide are pushing towards the fault-tolerant era, I'd like to give you a very explicit case study. And that case study is this. It's the simulation of a water molecule. Now, of course, I'm not making the claim that simulating a water molecule is a commercially interesting problem. It's a toy problem at best. But it's a problem where I can be very explicit, numerically explicit, about how NISQ and fault-tolerant quantum computations perform. And it's also the kind of simulation that should be very easy for a quantum computer. After all, quantum simulation, molecular simulation, was the original motivation for building quantum computers in the first place. Okay, all right, so I'm going to give you very explicit numbers for how NISQ and fault-tolerant quantum computers perform for this simulation task. But of course, there are a whole list of technical assumptions that go into those numerics. You can see them here if you're interested. But I'm going to highlight just a few. So assumptions on the hardware side for the numbers that I'm going to show on the next slide. I'm going to make the assumption that the physical clock rate of your quantum computer is about 100 nanoseconds to carry out a single operation. That's very ambitious. That's about an order of magnitude faster than current superconducting qubits. It's about 3 or 4 orders of magnitude faster than current trapped ion qubits. And so I'm going to make the ambitious assumption that your quantum computer is much faster than quantum computers we have access to today. Secondly, we've heard a lot about error mitigation over the course of the last 2 days. It turns out that the price you pay for error mitigation is to slow down your computation. And that will be bad for the numbers that I'm going to show. So I'm going to make the ambitious assumption that your qubits are so good that you don't need error mitigation. And thirdly, I'm going to try and be as optimistic about NISQ algorithms as possible. I'm going to assume that the time it takes to measure and reset your qubits, to calibrate your device, and the latency in sending data to and from the chip is exactly 0. On the algorithm side, the assumptions I'm going to make on the NISQ algorithm that's running is based on the paper that you can see at the bottom of this slide by our friends at Zapata Computing. I would thoroughly encourage you to go and read that paper if you're interested in more technical details or to ask me afterwards. And on the fault tolerance side, I'm going to use the best available state-of-the-art algorithm for simulating this molecule available to us today. And we're going to compile it using some proprietary hardware to PsiQuantum. Okay, so given these assumptions in this simulation task, how well does a NISQ algorithm perform? So a single evaluation of a NISQ circuit for this problem looks like this. So it's a quantum computation that requires 80 physical qubits, and it requires a circuit depth of 400. So the layers of operations that you're going to perform is about 400 operations. Given those 400 operations and the fact that this thing is running at 100 nanoseconds, that's a 40 microsecond evaluation time for this circuit on the NISQ computer. That's very good. However, this isn't the entire computation for the NISQ device. As we mentioned on the first slide, you have to repeat this circuit many, many times. And in fact, how many is many? Well, it's many. So the number of repetitions that you need to build statistics from this circuit, given that the output of the computation is stochastic, is what's called shot noise limited, which means that the number of repetitions you need is usually very, very large. So in this case, it's about 2 billion repetitions of this circuit to build statistics with high confidence. And so the runtime goes from about 40 microseconds to about 22 hours. But of course, we're still not done. Not only do you need to repeat the same circuit many, many times, you need to optimize the circuit in order to find some molecular property of interest. So in this case, the ground state energy of the water molecule. And even by very optimistic assumptions, you'll need hundreds of repetitions of this outer loop, this optimization. And so a 40 microsecond evaluation for a single circuit rapidly becomes a 3-month evaluation for the entire algorithm. Now, of course, on the fault tolerance side, if you want to run this algorithm on a fault tolerant machine, you're going to need many, many, many more qubits. So in fact, running the best state-of-the-art fault tolerant algorithm for this problem looks like this. You need a machine with about 3 million physical qubits, 3.2 million physical qubits to be precise. From those physical qubits, you derive 637 logical qubits. The circuit requires the operation of about 6.5 billion operations, and it runs in about 18 hours. Now, if you're particularly astute and you've been paying attention, you'll notice something interesting about the numbers on this slide. And that's if I take 6.5 billion operations and multiply it by the clock speed we stated earlier, which was 100 nanoseconds, I don't get 18 hours. I, in fact, get something like 10 minutes. So why is the runtime of this algorithm 18 hours? Well, the runtime of this algorithm is 18 hours because an operation for a fault-tolerant machine is different to an operation for a NISQ machine. And in fact, an operation for a fault-tolerant machine is much, much slower than an operation for a NISQ machine. And you might think that that's a bad thing for fault-tolerant quantum computers, but we've already seen that the runtime of this algorithm is significantly faster than the runtime of the NISQ device. So why is there some speed up here? There's some speed up because the fault-tolerant algorithm has access to subroutines and algorithms that are just not available to you if you're running a NISQ device. The kind of algorithms that you can deploy on a machine of this scale are fundamentally different to the kinds of algorithms that you would deploy on contemporary hardware. And that's where the speed up is derived. Okay. So one other thing I'd like to mention is that not only can we be explicit about the performance of large-scale fault-tolerant quantum computers, the algorithms that we will eventually deploy on those machines have been optimized significantly in the immediate past. So just in the last 5 years, so let's go back to the start of 2016, and look at how these algorithms have advanced. So each green point on this graph corresponds to roughly the area of the blue rectangle we saw on the previous slide as a measure of the amount of computational resources you need to solve this task. Since the start of 2016, this metric has been decreased by about 1 billion x. That's the kind of optimizations that we're capable of, even in the absence of being able to deploy these algorithms on large-scale hardware. But one other interesting thing to note about this data is that for all of these points, the advances in optimization have not come from quantum algorithms experts working in isolation. They've all come about by quantum algorithms experts collaborating with computational chemists and optimizing algorithms by learning more about molecular simulation and about computational chemistry. And so this is a singular piece of evidence that the only advances that we will meaningfully make in developing and deploying these algorithms is by working in tandem with domain experts. And so you might think, well, all of these companies have a roadmap to 2030, at which point large-scale fault-tolerant quantum computers will be a reality. So why not wait until then? Well, there are a couple of reasons not to wait until then, and you can see that from this graph. So all of these points have been the result of collaborations between private sector companies and computational chemists, domain experts. But the contributors to all of these points have been building expertise. They've been building expertise, they've been building IP, and they've been getting ready to deploy these algorithms when the machine arrives. And so they're likely to be front of the queue on day one when we have fault-tolerant large-scale machines. Okay. All right, let's go back to the thesis of the piece. So I hope I've convinced you of 3 things in the last 20 minutes. One is that ultimately, the performance of NISQ algorithms is limited in lots of ways, and that useful applications, as far as we're aware, require large-scale fault tolerance. And we saw that with the simulation task that we looked at earlier. Secondly, the algorithms that you can deploy on a fault-tolerant machine are fundamentally different to the algorithms that you will deploy on a quantum device today. And therefore, expertise that you generate in exploiting and developing NISQ algorithms now is not the same expertise that you will need in the era of fault tolerance. And lastly, if we're going to realize the full potential of this future paradigm of quantum computing, we have to co-design algorithms with domain experts. It's not enough for quantum applications researchers to act in isolation. Okay, thank you.